In this video, we're going to look at a method of working out the square root of our integers. Now, we're going to use something called the Babylonian method, and this method is reputed to be over 3,000 years old, which is interesting in itself. And I do suggest you go into Wikipedia and you stick in Babylonian method, and it will have a nice bit of history behind it. But we want to go on with this video and generate our function. So let's have a quick look at some of the mathematics, and then we will move on to an example, and then we will code it in Python, and then we'll take a Python code and then we will code it in our assembly language and run it on our machine. So I'm going to assume you understand the idea of a square root. If we have a square root of 49, the answer is 7. What it means is that there is a unique number multiplied by itself, which will give the answer 49. So 7 times 7 is equal to 49. We can write it as the number b, in this case is the number 7, is equal to the root of a. In this case, a would be 49. We can also write it as b equals sqrt a. Now, the Babylonian method is a nice and beautiful little method, and it really is the hinge, or the main point of mathematical point here is that we can write the number a here, and we can write the number a as x times a upon x, because the x's will cancel and we're just left with the a. But we also know that the value of a can be written as the root of a times the root of a. So take your time, just make sure that that makes sense to you. Now, the simple point here about the Babylonian method is that if this value for x was to go up, then in order for this equality to hold, the value of a upon x must go down. So there's nothing new in that, it's what the equality sign means in mathematics. So equivalently, if the value for our x was to go down, then in order for the equality to hold, the value a of x, a divided by x, must go up. So we could rewrite that and say that if x is greater than root a, then the a upon x will have to be less than root a in order for this equality to hold. Equivalently, we can say if x is less than root a, then a upon x must be greater than root a. So just take your time and think about that and make sure it makes some sense to you. Now, we could redraw this in a number line. We could have a number line here, and we could have a point on the number line. Now, that point in the number line could represent root of a. So again, we could choose a value a upon x which is less than root a, and we can choose a value of then x which would have to be greater than root a in order for the equality to hold. Equivalently, we can write it the other way. We can say that x is less than root a and a upon x is greater than root a. Now, the thing to note here is that either way, what happens is that the root a is going to be bounded by the value of x and x upon a. So what we can do is we can choose another value between these 2 points, and the other value between these 2 points is going to, the square root is going to sit in between these values. So we can choose another value, and the way that we choose the value is that we choose it by averaging out. So what we do is we take our value for our xn and we add on the value a upon xn, and then we divide it by 2. So really what we're saying is we know the root of the value somewhere between these. So what we can do is we can take an average point between these two, and we take the average point by taking the xn adding the a upon xn and then dividing it by 2, and this is the average, and this becomes our new point, x of n plus 1. And again, the x of n plus 1 is going to sit somewhere inside here. And again, we can work through the same process, and we can look at a point here for our new x of n plus 1, and again we can look at taking a value x less than that, therefore a upon x will have to be greater, or vice versa. But either way, the square root again is going to be bounded by these 2 points. And then we can take the next iteration of this, and the square root is going to be bounded by these 2 points. And you can see with each iteration, we're going to get closer and closer to the square root. So this is the idea behind the Babylonian method of generating the square root of a number. Now don't worry if you're looking at it and thinking, that's a little bit confusing. What matters is that we can go ahead and we'll actually go through an example, and sometimes from the example it becomes more obvious. And also what matters really is that we can code it and we can get it into our machine. So here is an example where we want to find the square root of 49. So a is the number 49. We have our algorithm here. Now we have to pick a first guess for our answer. Now if we're looking for the square root of 49, we know that the answer must be somewhere between 1 and 49. We know the answer isn't negative because we're not allowed to take the square root of negative numbers, and we will have to build that into our algorithm within Python and our assembly language code. So we know that the correct number is between 1 and 49, so we have to take a guess between that. Now what we are going to do for our algorithm is we are just going to take the first guess as the actual number a. Okay, so our first guess is going to be the number 49. Now we know that that isn't the correct answer. The correct answer must be less than that, but it's also got to be greater than the value of 1 in this instance, because we are only doing it with integer values. So we'll put the numbers in. So we're going to have x2 is going to equal 49. So 49 is just our first guess, plus the value of a, which is the number we're wanting to work out the square root of, which is 49, divided by, again, our guess, which is 49, all divided by 2, which is 50 divided by 2, which is 25. So if we then take this and we put it down into our next iteration, we're going to have the value 25 now becomes our next guess. So we're going to have our 25 plus 49 divided by 25 all up in 2. Now a thing to note here is that whenever we divide 49 by 25, we get 26.96, but we don't have these floating point numbers. We only have our integer values. But it doesn't matter, because the way the algorithm here is going to work for our integer values is that we're going to take the floor of the division. So for example, this 26.96 will actually be the value, just the value 26. So we're going to have 26 divided by 2, which is 13. And then we put 13 in, and again we work through to get the next term x4, and then we work through to get the next term x5, and you can see here we are already actually at the answer. Okay, but we'll go through the next term again, and you can see here that we get the same answer again. So what has happened is that we have generated the answer by coming in from both ends, until eventually when we get the correct answer, we get the correct answer twice. And we know when we get this twice, we've actually got the final answer. So that's a simple algorithm, you can work through it again for maybe for a value of 36, and the square root is going to be the number 6 or some other value. Now another thing to do here is to, on the right hand side, we can see how we're actually working, generating the square root by coming at it from both ends and slowly, with each iteration, getting closer and closer and closer from above and below. And you can see the above and below results here. So our first guess was 49, and the bottom number for it would be 1, and the term in between is 25. And then the next value is going to be 25 to 1, which is 13, and the next one is 13 to 3, and the value in between is 8, and the next one is 8 to 6, and the value in between is 7. So you can see here we're coming at it from the right hand side from the top and the left hand side from the bottom, and we're converging on the square root, which is a value of 7. So now we know how this works. Let's go ahead and we'll see it actually working in Python. So here is the algorithm written in Python. We're going to have a little function here, and we simply have the input value n. So n is the number we want to work out the square root of, for example 49. We know that the value for n can't be negative, and in fact we know it can only be an integer value. So we can check and see if n is less than a value of 1. If it is, then we can generate an error. Now we can generate our first guess, and we'll make the first guess the actual value n. So this is equivalent to making our first guess the number 49. And we can jump through our little iteration here, and I'll leave you can have a little read of that yourself. And we've got the number here, so we can change our number here, and we can bring out our result, and we can print that result out. Okay, so it just follows through the algorithm, and we may put it in like this, or we may change it slightly with our assembly language code. So let's see this actually running in Python. So we have the code here actually within Python, and we can run the simulation, and lo and behold, it comes out with the integer square root of 49 is 7. So the algorithm does work. Now let's take our algorithm and code it into our own assembly language. So we have here our assembly language code for our Babylonian square root algorithm. Now before we talk through this, one thing to note is that whenever we work out the square root of a number, we are going to get a positive value and a negative value. So for example, the square root of 49 is plus 7, but it's also minus 7. So minus 7 times minus 7 is plus 49. But what we do is we just work out the positive value. If you want access to the negative value, you can just take the positive value and you can generate that negative from it at the calling function level. So that said, let's talk over the rest of the code here. On the right hand side we have the calling function, on the left hand side we have the actual subroutine. So let's talk through the calling function first of all. We're going to push a number n onto the stack. So n is the number we want to work out the square root of, for example the square root of 49. We're going to jump to the subroutine called math_square root. So this is the subroutine here, and you can see it's just a memory location. So it's a memory location within the ROM, and I've picked this and I've taken note of it within our ROM's memory map. So we jump over to this location here. It runs through the subroutine for generating the square root, and it returns a result, and it puts it into a memory location which is called result. And then it finishes off the code, jumps back up to the calling function, and then we load the result into register R5 just for convenience so we can see it. But of course, you can do whatever you want with that result which sits in memory. And then the program ends. So now let's talk through the actual subroutine here. So the first thing we're going to do is we're going to save the value of the registers that we're going to use. So we'll save R0, R1 and R2 in some temporary memory locations, and then we will restore them at the very end once we've worked out the final result. So we're going to pop the return address off. We're going to pop the register R0, and register R0 is going to contain the value of N. Okay, so that's in this. Let's say for instance we're using 49 as the example. So we're looking for the square root of 49, so N is 49. So the first thing is a bit of housekeeping. We want to make sure that we don't have numbers which are less than 1. Okay, so we don't want fractional numbers that are positive, and we don't want any negative numbers. So we're comparing the number 1 with R0, and we're going to jump if A is greater than that value to trap A. So this will jump down to trap A, and it will give us a new trap value. So this new trap value will be a value of 5. Now what I decided to do in all of these was, once the trap occurs, we will just actually finish the code. Okay, so we can just jump to the end, so it just ends the code there and then. It doesn't clear off any of the registers or anything, because we're just finishing everything. So it stops at that point. Now if the input value N is a value that is greater than or equal to 1, it comes down and works through the square root algorithm. So the first thing it's going to do is take a copy of N and put it into a memory location which I've called guess. So this is the first guess at our square root. And the very first guess we're going to make is that the square root is actually equal to the number itself. So for example, if we're looking for the square root of 49, we take our very first guess and we say, well, is the answer 49? Okay, so R1 becomes the guess. And then we work in through the subroutine. We do the division, R0 with R1, so that gives us, R0 will give us N, and it will be divided by the guess. Okay, and remember, when we go through these divisions, it's a floor division, so it'll divide out and it will go down to the lowest integer value. And then we go on to the next line here. We need to load a copy of guess back into R1, because whenever we go through this division, it's going to replace R0 and R1. So R0 will give us the actual division number, and R1 would be the remainder. So we're going to have to replace the value in R1 with that value of guess, which again was 49. And then we can add R0 and R1, so we'll have guess plus N divided by the guess, and then we can shift the whole lot right. Okay, so we're going to shift R1 right by 1. So when we shift it right by 1, it's equivalent to a division by 2. So shift left would be multiply by 2, shift right would be divide by 2. So we're going to shift it right, and then we're going to put the answer into R2. So that's going to give us the little bit of arithmetic we need in order to work out the next value. So the next value now sits in R2, and we can store the contents of R2 in a memory location which I've called the next guess. Okay, so what we can do is we can compare the original guess 49 with the next guess. Now if both of those are equal, then we know that we've found the square root, and at that point there we can just head down to the return and we can store the result from R2 into the memory location called result. Now if that isn't the case and those two are not equal, it'll move on to the next line. So what it does is it takes the next guess and it stores it in guess. So that's equivalent to taking the number 25, and we're now using the number 25 instead of the number 49. Okay, so that number 25 then is going to be used in the next iteration of the algorithm. But of course, we're going to have to load the values in. So we're going to load again the value n, which is our original value that we want to take the square root of, and we'll put it into R0. And we're going to take the guess, which is the new value 25, into register R1, and then we're going to jump back to the guess routine. So we get back through that, and we continually work through that loop until eventually the guess is equal to the next guess. Whenever those are equal, it means we jump to if equal to return, we go to the return, we store the result in result, and then we restore each of the registers R0, R1 and R2 to the original values that they had before the function, the subroutine, ran. And then we're going to jump back to the calling function. When we jump back to the calling function, we come back to this line here, and at this point we're going to load the value from result in memory into register R5, and then the program will end. So that's the end of this. Let's go ahead and we'll put a value in and we'll see it working. So I have loaded the code into our CPU. Now let's run it. Now I have set up the simulation to run a little bit slower, so we can potentially see a little bit more happening here. But of course you can always download all of these simulation files from the resources section and run them as slowly as you want. And of course you can run through the values individually with every single clock pulse just by pulsing the little clock here. So let's run through this just now, and I'll try and talk through as it happens. So we're going to load up all of the initial variables with a value of 0, so that's what's happening at the moment. And then we're going to work through R0 and R1 in order to generate the actual value. So that's the number 49 in hex, and then we go through the addition. The division ends up with a value 25, which is the next value, and then when we go through the next loop we get a value of D, and then the next loop is 8, and then the next loop should give us a value of 7, and that's a 7 there. And when both of these are equal, we see 7 is equal to 7, then we know we're finished, and we put the result into R5 and we clear off the R0, R1 and R2, so it goes back to the original values. So now the value in register R5 is the number 7, which is a square root, and that number 7 is also held within memory. Now if you're looking for some more historical details, you can always go online, and I suggest you check out YBC 7289. This shows an ancient tablet which the writing has been dated to 1600 to around 1800 BC, and it shows that they were able to work out the square root of 2 up to around 6 decimal places. Now it doesn't say that they used the Babylonian method that we employed here, but they may well have done that. So if you're interested in some of the history, I do suggest you go and have a look online and chase this up, because there's an awful lot of interesting details there. So that's all for this video. We will move on to another function in the next video. Goodbye.